Welcome to lecture 3 on atmospheric dynamics. So in the previous lecture, we are discussing under non-inertial reference frames and apparent forces. So in this lecture we cover the Coriolis force and the curvature effects. So as mentioned, in my previous lectures also, this the content is taken from an introduction to dynamic meteorology, fourth edition by James Holton. So the Coriolis force and the curvature effect. So what do you mean by the Coriolis force? We have to understand here. So it is a force experienced by a mass in a rotating system, and that force acts perpendicular to the direction of motion and to the axis of rotation. So the Coriolis force actually changes the direction of motion but not the speed of motion. So let's see how we can understand mathematically. So the earth revolves around its axis for every one side real day. So one side real day is equal to 23 hours 56 minutes 4 seconds, which is equal to 86,164 seconds. So from that we can calculate the angular frequency, which is given by omega is equal to 2 pi by t, so which is 86,164 seconds, and which is equal to 7.292 into 10 power minus 5 radians per second. So which is a constant. Now to understand the effect of Coriolis force, so let us take an example here. So suppose a unit mass is located initially at an altitude phi, which is mentioned here as phi. Okay, and now and also we understand that it is moving with a zonal velocity u, and due to impulsive force, let us imagine it is being displaced to an altitude or a latitude. Okay, so then definitely we will find some change in the distance of the mass from the axis of rotation. Here in this case, when it was at this position, so we can say the distance of the mass from the axis of rotation is r, and after displacement it is r plus delta r, and the displacement that is made is delta y. Okay, so the radius of the earth is mentioned as a. Okay, so the figure it is given here, the relationship of delta r and delta y, which is equal to a delta phi. So that is obtained from this triangle for an equatorward displacement. Means if the mass is being displaced towards the equator. So that's what. So when the mass is moving in the eastward direction, okay, so when it is being displaced, the angular momentum is conserved. So when we try to understand about the angular velocity, which is given by omega plus u by r, so which is called the absolute angular velocity, where u is the zonal velocity relative to the surface of the earth. So now, because in that formula omega plus u by r, omega is constant, to preserve the angular momentum or to conserve the angular momentum, u must be changing. So the mass is being displaced, although some zonal deflection force is acting on that mass. So let us try to understand how the angular momentum is conserved. So if for example, when we know well about the formula of angular momentum, which is given by m r square omega. Since we are discussing here with respect to unit mass, we will write r square omega. So r square omega, so r square we have written, and in place of omega we are just writing omega plus u by r, so which must be equal to. So because as we discussed that for the angular momentum to be conserved, there must be some change in the zonal velocity as well as the distance of the mass from the axis of rotation. Accordingly, So this expression is being adjusted to as u plus delta u and r plus delta r into r plus delta r whole square. So where delta u is the change in eastward relative velocity after the displacement. So now after solving this right hand side expression of equation 1 and removing the second order differentials, okay, or neglecting it, so you obtain delta u as minus 2 omega delta r minus mu u by r delta r. So here from this diagram r is given as a cos phi. From this triangle we can write r is equal to a cos phi. Now when delta t tends to 0, we have to observe how delta u by delta v will be, and delta r from this diagram you can understand that delta r is equal to minus sine phi delta phi. So when you try to divide the equation 2 with respect to t and also substitute delta r as minus sine phi delta y, we will obtain du by dt is equal to 2 omega sine phi plus u by a tan phi dy by dt, which is equal to, so in this dy by dt we can simply replace with the meridional velocity, we can say, so which is represented with the letter v. I can write it as 2 omega v sine phi plus u by a. So so this dy by dt is multiplied with this term also, so that you will obtain uv by a tan phi. So this is for meridional displacement. Suppose if the mass is being displaced vertically, so how the delta r is written as plus cos phi delta z. So if that is the case, so you can also find out du by dt, so which is equal to minus 2 omega cos phi plus u by a. So when you substitute delta r is the cos phi delta z, so you will obtain like this, where you're replacing the dz by dt with w, so which is called the vertical velocity. So minus uw by a. So we obtained the equations. So now, so this in this equation in 3 and equation 4, this 2 omega v sine phi and minus 2 omega w cos phi, so so are the Coriolis force for meridional and vertical motions respectively, and these are called as metric terms, the uv by a tan phi and as well as minus uw by a. So and these terms are due to the curvature effects with respect to the curvature of the Earth's surface. So let us now discuss the meridional components of Coriolis force. So let us assume the object is set in eastward motion by an impulsive force. So now the object is rotating faster than the Earth. So it means the centrifugal force is increased. So now how much excess of centrifugal force we can expect, we can estimate it. So you can write omega plus u by r whole square r, which is the angular momentum, minus omega square r. If you do that, you will obtain 2 omega u r by r, so this is the r vector, so u square r vector by r square. So the terms on the right side, so they actually reflect the deflecting forces which are perpendicular to the axis of rotation. So the meridional and vertical components of these forces, okay, so from this figure B you can understand that so you can understand that the components of this force is being given here. So now dv by dt is given as minus 2 omega u sine phi minus u square by a tan phi. So this is considered by taking those components and trying to do similar to the way we have got the expression for du by dt from this equation number 2. The similar way you can also obtain for dv by dt as well as dw by dt. So now these first terms on the right side, you can see minus 2 omega u sine phi and 2 omega u cos phi are called the meridional and vertical components respectively for of the Coriolis forces in the zonal motion. Okay, because we have initially considered the movement of the object in the eastward direction. The second terms are again are due to the curvature effects. So for synoptic scale motions, okay, so we can understand that so the zonal velocity is very less than omega r. Okay, so then the last terms in 3 and 6, equation 3 and 6, which are again rewritten over here. So we have obtained equation 3 as a du by dt and equation 4 for dv by dt. So in both the terms, the last terms uv by a tan phi as well as u square by a tan phi can be neglected when compared with the omega r. So now these equations are now reduced to du by dt. So this is not to represent Coriolis effect. It is written as CO, which is equal to 2 omega v sin phi, and from this expression you can write dv by dt CO, which is equal to minus 2 omega u sin phi. So we are neglecting that. So from this expression, so you are taking out this 2 omega sin phi alone, and you are representing with the a variable or a parameter. You can call it as f. And in the same way here, minus 2 omega u sin minus 2 omega sin phi as minus fu we are writing. So where f 2 sin phi is called the Coriolis parameter. So for example, if the object is moving in the eastward direction, so the Coriolis force make the object to deflect towards its right. The same way, if it is moving towards the west, the Coriolis force makes the object to deflect towards the poles. So in either cases, the deflection is to the right, the direction of motion in the northern hemisphere, and to the left in the southern hemisphere. So then we have the vertical component of the Coriolis force, which is given by dw by dt, which is equal to 2 omega u cos phi plus u square by a. So that vertical component is very much smaller than when compared to the gravitational force. We can neglect it. So now the x and y components in the equation 8 and 9, again it is again the rewritten here. So du by dt Coriolis component, which is equal to 2 omega v sin phi is equal to fv, and dv by dt is given as minus 2 omega u sin phi, which is equal to fv minus fu. So now combining these equations into vector form, we can write it as dv vector by dt is equal to minus f k cross v, where this v vector u and v, which are the horizontal velocities. Okay, so this f minus f k cross v tells you that is a vector rotated 90 degrees to the right of v and shows the deflection character of the Coriolis force. And now from these equations we can understand that so the Coriolis force can only change the direction of motion, not the speed of motion. Thank you.